Hi, it's Ryan. Today we're going to do a little vector review, so that's what I'll title this. So we're going to talk about vectors. Vectors are important. We use them pretty much constantly in our class, and people probably give them a little bit more credit than they deserve, meaning you probably have a little bit of anxiety about vectors right now. You haven't used them a lot, but they really are very straightforward. No pun intended. So a vector should always have a magnitude and direction. So we could note that. Vectors always have magnitude and direction. Remember, magnitude is the fancy math word for amount. We don't say amount because it could mean multiple things. We always use the word magnitude. And really, we have multiple ways to represent a vector. So let's say that our vector we're going to talk about today might look like this. A. So there it is. So there are options for how we can represent this vector. So what I'm going to do, I'm going to take this vector and I'm just going to drag it around with me when I need it. So I'm just going to copy that. And so now when I need it, I can use it. Anyway, the point is we have options. Option 1. Option 1, we can represent this vector A. A. It might represent something that is a displacement. So maybe it could be in meters. Maybe this is 21 meters. And we could say that it's going north. And actually, let's give an actual amount here. Let's say that this is going theta on some angle theta there. Keep in mind, we could note this since it is kind of our intro here. This is the horizontal. And that representing 0 degrees. So if our vector was just horizontal like that line, then our vector would be at 0 degrees. In this case, we could say theta. So we'll just say theta degrees north of east. East. Or you could just write northeast, like that. NE implies north of east. So that's one option. Another option is actually very pictorial. You could rely on a picture to give an answer. Seems crazy, I know, but it's true. So we could anyway, I guess we can. I'll just redraw it. So we could say that A has a magnitude. That symbol means the magnitude of A. So we could give this vector as a picture, A. And then we could say that A is 21 meters. That is an actually acceptable form to the answer that I would take. If you're going to do this, it's important to give a coordinate system. So you define maybe east and north in your coordinate system. And we could show the angle theta. So that would be an acceptable way to answer. Most people don't do it this way. Most people tend to run away from drawing pictures for whatever reason. This next option, which is perhaps the easiest option, option 3, this is the unit vector method. And so in order to use the unit vector method, we have to define for you a unit vector. A unit vector is a vector, of course, a vector with magnitude of 1, that gives direction. That's what a unit vector is. And so the unit vectors we'll usually be using, so I'm going to make a little table, the unit vector and the direction that it points, direction. The symbol we use for unit vectors, the symbol would be A with a hat. So really the symbol is the hat. That means unit vector. So a hat would be the unit vector that points in the direction of A. And I'm actually going to show you that first before I show these unit vectors. So if we have A like that, there was A. Now that might be slightly off, but doesn't matter. Our unit vector looks like this, A. So A, our unit vector, has magnitude 1, and it points in the direction of big A. In general, so we could say generally, the unit vector A is defined as the vector A divided by the magnitude of the vector of A. So that's just the mathematical definition for any unit vector. So I like to give that to you, though we really never, honestly, will probably use it. I just like you to know. So the unit vectors that we use, the unit vector will be I with a hat, J with a hat, or K with a hat. And each of those represent the X direction, the Y direction, or the Z direction. Now in our class, we won't really be using 3 dimensions until we get to Physics 2. And so really, we are going to mostly be using these for Physics 1. And so we can represent A in the terms of its unit vectors, and I'll show you what I mean by that. So A, there it is, A. A has some amount that is horizontal, A in the X direction, and it has some amount in the vertical direction, A in the Y direction. And so we can always represent A as a vector using the unit vectors. We know that A points AX in the X direction. This amount in the X direction, and we know that it points this amount in the Y direction, AY in the Y direction, and we add them together to get the expression for our vector. So you can write a vector expression in this form, or you can write it in this form, and either one gives me all the information I need about the vector. I think in general this ends up being the easiest one, because normally you don't have to solve as much. I guess there's one more note we could make. We talked earlier that the magnitude of A, the amount of A, is given by that expression. But now, thinking a little bit more mathematically, when we look at A here, aren't we creating a right triangle with AX and AY? Well, if that's the case, then we know that the magnitude of A is always equal to, and we'll use the square root of AX squared plus AY squared. And that's secretly just the Pythagorean theorem, isn't it? So one more note on vectors before I talk more about trig for you. One more note on vectors. We always can add or subtract vectors. So we might have vector A, and we might try to add a different vector, maybe vector B, that looks something like this. And so what we really can do whenever we add vectors, there are a couple ways to do it. We really do it diagrammatically, and I'd like to show you that first, but that will give way to the mathematical form. So we'll say diagrammatically. And this is kind of a rule that's always true. You can always move your vectors around as long as you keep them the same length and pointed the same direction. And so let's also label that this is at some angle theta, and maybe we could show that this is at some angle phi. So diagrammatically, we can take our A vector and we add vectors tip to tail. So we can pick up our A vector. I'm going to give myself more room here. And we can then pick up our B vector and put the tail of it on the tip of A, like so. So A plus B will give our resultant vector R. And I'll do R in this color. R is just adding now from the tail of our first vector to the tip of our second vector. That's our resultant vector. And so if you really look at this picture, we have A broken into its horizontal component, AX, and its vertical component, AY. And we have B broken up in a similar way. We have an X component, BX, and we have a vertical component, BY. And as you can see, if we were to add all these vertical components together, we would get the total vertical component for R. So we can see that R, I'm going to use a different color than that. RY, and the RX gives us the resultant vector. But as you can see, if we were to add AY and BY, we would get RY. And if we add AX and BX, we would end up with RX, wouldn't we? So the picture looks a little convoluted now, but it gives way to how you can always add vectors mathematically. That means that if we say R is equal to, we would have to give the horizontal and vertical components, and those are given just by adding AX plus BX in the X direction, and AY plus BY in the Y direction, just like our picture shows, and that would give us the total R vector. Something to note is that B x is negative. And so when we substitute in our values here, we'll end up putting in a negative bx, and that would make rx and ry accurate, but rx would then be less than ax, like we want. So when you add vectors, you can just put together their components and then have your answer. You can also show it diagrammatically if you'd like. And we could work with these angles in here to figure out what this angle is. Another way to show this vector would be this angle. We could call it alpha. And so if we were to calculate the magnitude of r, it would just be the magnitude of r at alpha degrees. That's another way. So this is an answer, this is an answer, and it might be worth noting that the magnitude of r is just the Pythagorean theorem. Ax minus bx squared plus ay plus by squared. So that's a little bit of vector review, adding and subtracting vectors. But that really gave way as soon as we started talking about Pythagorean theorem and breaking A into its x and y components. What we need to talk about next is some trigonometry. Some trigonometry. Have you taken trig before? Did your teacher define it for you? Trigonometry is the study of three-sided figures. My bet is that most of you that have taken trig started trigonometry out with a circle. And I just think that's crazy. Trig should always be started with triangles, and that cute little unit circle that you started with is really just built off of two triangles anyway. But I'm not your math teacher. So we're going to talk a little bit about trig. And the reason we're doing this is that for any vector, you should analyze using trigonometry. So you should employ trigonometry to help solve. Or understand the vector. And so let's look back at A, vector A. There it is. Vector A, we said, was at some angle theta. Now we could say that there is a different angle, that if we create a triangle here, that this AX and AY, we could say that this angle is another angle we know, phi, and isn't phi equal 90 minus theta, right? 90 degrees. Here's our 90-degree angle. Anytime you're going to use a vector, you can always create a right triangle with it. And the real reason that we want to create a right triangle is so we can use trigonometry functions. And so we'll define a few of those for you. Sine of theta. Now, whenever we write sine theta, we're talking about this angle. If I wrote sine phi, we would have to use different side lengths. But we define sine for you, always the same. It's always the opposite side divided by the hypotenuse. And hypotenuse is the longest side of the triangle. Sorry, I misspelled it at first. Hypotenuse. And the hypotenuse is always opposite the 90-degree angle, just so you know. It's always opposite the largest angle, which is 90 in this case. But anyway, sine of our angle is always opposite over hypotenuse. So the sine of our actual theta here is AY over A, the magnitude of A, really. So I'll just be super careful and write that out. What is cosine theta, do you remember? It's adjacent, which just means next to, over hypotenuse. The side next to theta is ax. It's next to it, not opposite. So that means the adjacent over the hypotenuse would be ax over a. And of course, what is tangent of theta? Now, tangent of theta is sine theta over cosine theta, but that will end up being opposite over adjacent. And so in our case, it would be ay over ax. Keep in mind, if you knew phi and you didn't know theta, all of these would be different because we would have to do sine of phi, so opposite would be x, not y, and so on. But in general, these are your trigonometric definitions that you're always going to have to use. And of course, using the Pythagorean theorem, a magnitude, or the amount of the hypotenuse, is equal to the square root of ax squared, which is our opposite, or our adjacent side with respect to theta, plus ay squared. And that's the Pythagorean theorem. And so you'll definitely need to use those often. Anytime you want to represent a vector or solve vector math, you're going to end up probably having to use trig. And speaking of trig then, another way to represent a using the trig would be a cosine theta in the x direction plus a sine theta in the y direction. And it's worth noting this is true for this, only true for a above. I don't want you to memorize cosine is always x, sine is always y. That's a bad habit. And by chapter 4, that won't be the case. So you don't want to memorize this like it's always true, because that leads you to potential incorrect answers. So there's a little vector review for you, and some trigonometric review as well.